So I've got a HIWIN brushless servo motor, FRL series, and it has a 13-bit incremental, A naught, B naught, XX naught, plus 5 in ground. It is not just an incremental encoder. We do not have to just do wake and wiggle. There are Halls embedded in it. It's a wire-saving incremental encoder. We just have to set some bits properly. But let's take a look for the motor data. So we can take a look online and we can find the motor information. The one I have has a brake with a holding brake, and it gets a little warm with the brake, so I'll show how to do PWM brake on this. But you got your basic motor data here, Newton meters, Newton amps. It's amps RMS 1.7, and the torque constants and the inertia. So in CME, we can enter the motor data. It's a 10-pole motor, 0.21 with the brake, kilograms, centimeters squared, 1.9 Newton meters, 0.68 Newton meters divided by the amps RMS, and you get the Newton meters per amp RMS. Converts to amps peak because Copley's in peak, motors are in RMS. And then the volts per radian per second, same value as the K sub T, and then the inductance and resistance entered. And this is a theoretical top speed. It said 5,000 for max speed, so we'll use that for a velocity limit. And then you press calculate to get the initial tuning parameters. But first, most important, is picking the right detail. Brushless rotary. This one has a brake, and it's a Sanyo Denki wire saving. Well, really, it's not a Sanyo Denki. There's a couple of bits that are different, but we'll pick this one because it gives us the Halls, and it's a 10,000 count, 2,500 line. I have the loss detection turned on. Do not ignore your feedback. And then I'm just doing position mode, and then we'll see how this works for us. I'm just going to see the mode is disabled now. So for the phasing, this is the critical factor here. I've got current loop values, from calculated or tuning, but so I can go to Tools, Manual Phase, and I can enable the drive, click, the brake comes on. I can rotate the current vector now. I have to rotate this vector 5 times to go for a 10-pole motor, so 5 electrical cycles. And you can see the Halls are decoding. I'm going forward. I'm rotating the motor forward. The counts are going up, and I get 10,000 counts for 1 rev of the motor. And you can see when you go reverse, the red indicator leads in both directions. I've got the Hall selected as WUV. I don't see any offset here, but if you had some offset, you'd get a wicked lead or a wicked lag. I just wired in a logical manner here and selected the invert the motor, don't invert the feedback, and WUV for the Hall decode. And it looks slightly leading in both directions with no load, so that's good. Nothing changed. We'll say okay. So let's take a little look at the motor specifications from their catalogs. I got some. So the HIWIN FRL motor, you can see here there's a space holder for, this one has a 5, 13-bit. There's a 17-bit absolute and a HIWIN 17 incremental encoder. I haven't tested the 6 or the 4 yet, but this should be an absolute encoder. And then, of course, I found some more data from one of the distributors on the time it takes to turn on the UVW. So I get a 20 millisecond window here. So from power up, and so that's what the special bit's for. Oh yeah, let me go back and make sure we set that. And so the note will say set 0x12A, and set these bits 16 and 17. And you can do S for set and then enter. What was the value there? Get from hex 30000. So I'm going to set 0x30000. Good. This is what you have to do in order to make this work. It's not a Sanyo Denki, it's a HIWIN. So there's some new bits to take care of that. And firmware 4.60 or 4.36 should be fine, but let's finish reading the note here. Yeah, so we gathered the data specifications. I found this online too. They had a speed torque curve. Here's some details about the encoder. Here's the wiring for the motor, UVW, and then there's a brake. These are pinned out on the smaller connector here. I've got this one with the brake. You can see the color codes too, red, white, black, good logical order. And here's the encoder. So A naught, B naught, Z naught. There's a plus and a minus here. So 2, 3, 4, 5, 6, and 7. And then 2 is ground, pin 1 is 5 volts. I got the feedback here, and you can see the color decoding. So the red is 5, and the black is ground. And then we've got X and X naught yellow. We got A and A naught white, and white black for A, and white for A, and white black for A naught, and then B and B naught with the green and then the blue, and then here's the pin out. So you can look at the connector and see the pin out, and this is going to a 26-pin Copley plus drive. So the standard AA naught, BB naught, XX naught, plus 5 and ground with a shield. Make sure the shield is not connected to the motor case. But here's the critical factor. So it's a normal encoder type 21, which is wire saving. By default, we set the bits for the Sanyo Denki because that's what we selected. We'll add HIWIN to the CME later, maybe under username and password, but not trying to promote HIWIN, but just trying to drive their motors. And so this is the critical factor here. 12A needs to have these bits set or it will not work. And so there was a previous firmware set because the Hall offset, the encoder outputs reversed from the direction which we considered normal. Well, that was Sanyo Denki, normal for Sanyo Denki, but not normal for HIWIN. And then, of course, with this 4.01 or greater, so the production or the next level. Bit 17 also needs to be set, and then sample after 10 milliseconds. So that's the detail in the parameter dictionary. And then you get this screen, right, when you select wire saving and set that bit. And this would be for the absolute, but we don't have that here. And the other thing I wanted to show was there's a brake on this motor. It's 24 volt, and the motor seemed to warm up a bit. And so here's the default settings for out 5. But I decided to test out this new PWM brake output so I can fold it back to 12 volts. The frequency I used was 10 kilohertz, 200 milliseconds at 24 volts, and fold back to 12 volts. You can see the setting of the parameter based on the configuration of the bits. It's a bit complicated, but read the parameter dictionary if you want to learn more. But the cool thing was, as soon as I set this parameter in the drive, I get this configure button in the brake output, so I can more easily change the parameters here. And you'll notice on my voltmeter here, I'm actually measuring 14 volts. And there's a couple of reasons. The PWM frequency to the inductance may affect the voltage. I tried a lower frequency, but it tended to give me a lower voltage, so I put it back up. I think the max is 16 kilohertz, but there's an opto in here too, so that will affect the switching frequency. So there's two things kind of affecting the adjustments here. It's not so empirical of, hey, I set it to 12 volts, which is 50%. No, it's not going to be 50% with the different turn on and turn off time of the opto at whatever frequency. And of course, the inductance plays an effect in the brake too. So lower frequencies may not get the voltage up there properly, but the higher frequencies seem to get closer to the target. Anyway, so you can tweak it a little bit. If the voltage is too low, your brake will not hold. If your voltage is too high, you're just unnecessarily warming up the brake resistance here. And if you feel the motor, it's with the 14 volts. It's nice and cool. It's holding position, and it's been on for hours, and it's barely warmed up. So this PWM brake feature is very useful. Have a little bit of moment of time here, so I'll just check the bandwidth here. Okay, about 1 kilohertz, so I tuned it using the scope. The calculated values were pretty close to the inductance values or the resistance values. You can measure with an ohm meter. It is line to line, so that's good for calculated values. So there's an auto tuner, but I just do manual tuning. And on the velocity loop, yeah, we'll want to bring that back up. Like if the rated speed's 3,000, you got to enter this must be larger than that. So I'm going to set it to 5,000. I tune the velocity, VP and VI also. And then for position loop, I'm anticipating a large inertia because this is a pretty high, pretty beefy motor. So I'm going to dial down the proportional, assuming that there's a. Also, I brought in the filter on the V loop to 100 hertz, anticipating a large inertia, and then tuned up the loops. We'll see if we have time to make a move and settle. Okay, yeah, there's the move. We'll make a longer distance. So there's a 10 rev move, 100,000 counts. So this looks pretty good. You can give it a little bit more integral there if you want, but I'd say that's pretty good settling within. It's 10,000 counts per rev, so within 100 counts, you're doing great. There's a little ripple while we're moving. That's not bad. And then with the index, you could probably do home to an index. Have a few seconds left. We'll see what expires from this. And if you do the homing, you could set a positive and negative soft limit, and then make sure you put in a decel rate if you want to use soft limits. But yeah, that's basically it. Just make sure you do Sanyo Denki wire saving. In the future, we'll say HIWIN wire saving, and set those bits 0x 12A in hex. Get from flash, and forget. There we go. So there's the hex value. All right, thanks for watching HIWIN FRL motor wire saving 13-bit incremental.